today we are going to derive an expression for the magnetic field due to a current carrying wire of infinite length by using Ampere's circuital law. Okay. Now in the picture you can see there is a current carrying conductor which is extending up to infinity. So let I be the current flowing through the conductor in the upward direction, and we have already studied the Biot-Savart law and also the right hand thumb rule. According to the right hand thumb rule, if you consider a current carrying conductor such that the current is indicated upward along the direction of the thumb, then the folded fingers wrapped around the conductor will give you the direction of the magnetic field lines in the anti-clockwise direction. So at various points, at various distances from the current carrying conductor, there will be magnetic field. I have chosen one point A, which is at a distance small r from the current carrying conductor. So I am going to get an expression for the magnetic field at the point A, which is at a distance r. Okay, for that I have to use Ampere's circuital law. I will write the Ampere's circuital law in the mathematical form. So this is the closed integral of the dot product of the magnetic field and the line element vector. This is equal to mu naught times the net current enclosed, in the closed loop. That means if you imagine a closed loop around the current carrying conductor, that imaginary closed loop around this conductor is called by the name Amperean loop. Okay students, now the shape of the conductor is cylindrical. It is a very long cylindrical. So due to its symmetry, it is better if we have a circular Amperean loop. So this is the circular Amperean loop of radius r, so that the point A lies on the Amperean loop. So at this point A, the direction of the magnetic field should be tangential to the circle. Okay, because the current is upward, so that there should be anti-clockwise field, means then at this point A, the field should be tangential. Okay, now the Amperean loop accommodates the point A. At A, the magnetic field is B. Then you consider the portion of the Amperean loop. In space, you have to imagine as if there is a circular loop. Out of the circular loop, you imagine that is made up of small elements of length dl. One such small line element dl I have shown. This dl is a portion of the circular Amperean loop. Since it is associated with the magnetic field, this line element dl is also a vector. So this dl, okay, this dl is called as line element vector. And B, this is B is a magnetic field vector. Magnetic field vector. Now you can see in this picture that dl vector is also tangential to the Amperean loop, and B vector is also tangential to the Amperean loop, so that here the angle between these two vectors B and dl vector is equal to 0. dl is not a material medium, it is a portion of the imaginary loop, that's all. In that portion dl, there is a field associated with it, therefore dl is a vector. Okay students, according to Ampere's circuital law, the closed integral of B dot dl is equal to mu naught times the net current enclosed by the loop. Now here there is only one conductor which is enclosed by the loop, and there is only one current flowing through the conductor. So naturally the net current is nothing but the actual current flowing through the conductor. Is it not? Okay. Now the left hand side of this equation you see here, integral of B dot dl. So this is equal to closed integral. So this is equal to closed integral B into dl into cos of the angle between them is 0. So this is now equal to the magnetic field B, its magnitude will be the same at all points which are equidistant from the center. You take so many points on this Ampere loop, all points are at the same distance r from the center. Therefore, naturally the magnitude of B should be constant at all points, same at all points. Therefore, I will take B out of the integral. So, this is equal to B into closed integral. So, this is a closed integral of dl. Cos 0 is equal to 1. Now, dl is a portion of the Ampere loop. So, like this, there are so many other elements of the same length dl. If you add all the length dl on the Ampere loop, then the closed integral dl must be equal to the circumference of the circle, which is 2 pi r. So, this is now equal to B into 2 pi r. Okay. Now, the right hand side is mu naught into I net. See here, the net current is nothing but the actual current which is flowing through the Ampere loop. Okay, students. Therefore, now I am going to substitute for this left hand side is equal to B into 2 pi r. So, B into 2 pi r. This is equal to mu naught into the net current is nothing but the actual current flowing through the conductor. We need an expression for B. Therefore, B is now equal to mu naught I divided by 2 pi r. So, this is the magnitude. This is the magnitude of the magnetic field B at the point A. But actually, magnetic field is a vector quantity. And hence, in vector form, the same can be written as B vector is equal to mu naught into I divided by 2 pi r into, you can take n cap, which is a unit vector along the direction of B. So, you can take here along this direction of B a unit vector. So, this is in vector form. Okay, now in competitive exams like IIT and NEET, one question is definitely asked from this portion. So, for that I am going to show you one example. See here, I will consider an Ampere loop. You take this is an Ampere loop, and inside this Ampere loop now I am going to consider two conductors. So, this is one conductor, and here some current is flowing. And another conductor I am showing you, see here, in which some current is flowing in the downward direction. And the third conductor, another conductor is kept outside this Ampere loop. So, you can see now there are three current carrying conductors. Okay, like this. If in the first conductor 2 ampere current is flowing upward, in the second conductor 1 ampere current is flowing in the downward direction, and in the third conductor 3 ampere current is flowing in the upward direction. Now you look carefully, totally how many conductors are there? There are 3 conductors. But out of the 3 conductors, how many are placed inside the Ampere loop only is important for us. Because in Ampere's circuital law, the right hand side of this equation is mu naught times the net current enclosed by the Ampere loop. So, what is the net current inside the loop? We have to find out. So, the third conductor, since it is outside the Ampere loop, that is not going to contribute. Okay, therefore it is neglected. Only these 2 conductors we have to analyze. Out of the 2 conductors, you see one conductor is carrying the current in the upward direction, the other conductor is carrying a current in the downward direction. Therefore, what is the net current in this case? In this case, the net current I net or I enclosed is equal to 2 ampere minus 1 ampere, that is equal to 1 ampere. Okay, students, have you all understood? So, net current in this case is equal to what? 1 ampere only. And therefore, if you write Ampere's circuital law, means closed integral B dot dl is equal to 1 ampere. So, this is mu naught times 1 ampere. So, this is mu naught times 1. That is equal to simply mu naught. Suppose you take two conductors like this in the Ampere and loop. Another case I will find out. So this is one conductor, and another conductor is kept inside. In the first conductor, suppose if 2 ampere current is upward, second conductor 1 ampere current is upward. So in this picture, the current in both the conductors are upward. So what is the net current? It must be 2 ampere plus 1 ampere. It is 3 ampere. So in this picture, net current is equal to 2 ampere plus 1 ampere. So this is equal to 3 ampere. Like that. So accordingly, whether the conductor is carrying current in the upward or downward direction, you have to find the net current enclosed. Okay students, have you understood? Fine.